Welcome everyone. So welcome to this tutorial session 6. I hope you can see my screen.
Good evening, sir. Yes, sir.
Okay. So we'll be covering a few questions. So we'll be covering 15 questions for week 6. Okay. So today the question will be mostly based on root locus. Okay. So in the beginning, I'll be going through what is covered in week 6. Okay. If you have any doubt, so you can ask me there and there. Then we'll be doing questions. Okay. So in week 6, let me say what is covered in week 4, week 5. Okay, so we covered about the error constants. Okay, so in week 6, we looked at root locus. So how to plot the closed loop poles in the S plane. Okay, by using the open loop transfer function. Okay, so what is important? So how we got to those equations? So we have to follow from 1 to 6 step. Okay, so each step is derived from these two conditions here. Okay, so first if you look at the closed loop transfer function, okay, so this is the closed loop transfer function, right? And if you see how to get the roots or the poles of the closed loop transfer function, so see the denominator, which is 1 plus GSHS, you equate it to 0 and you get the poles, right? And also another form, it can be written as like this: GSHS equal to -1. So what we can say, so since GSHS, it's a complex, right? Complex equation, because S is sigma plus J omega. So -1 can be written as magnitude and the angle, right? So it can be written like this: 1 plus minus 180 degree, right? So it has two terms, magnitude condition and the angle condition. If any of the pole, if any of the poles satisfy this condition, we say that pole is the root of this 1 plus GS into HS, right? So these two are the conditions. And for this given GS HS transfer function, so we have assumed the open loop transfer function to be of this form, where K is a real number which can vary from minus infinity to infinity. But in this case, in this week 6, we have covered cases where K is greater than 0. Okay, and you can say Z1, Z2 up to Zm are the open loop zeros, and P1, P2 and up to Pn are the open loop poles here. So there are total of n poles and m zeros, okay, that you can see from this open loop transfer function. Okay, so we are just plotting how the closed loop poles are changing as we are varying K from 0 to infinity. Okay, so you'll be taking only positive values for K here. Okay, so already we have defined what is root locus. So it is a locus of closed loop poles as K is varied, right? So first it will be how many branches it has, right? So before that, like since we are plotting root locus or the poles in the S plane, so what are the properties? You take just a test point. Okay, so ST is a test point. Okay, if it satisfies these two condition, magnitude condition and angle condition, what we say is that pole lie on the root locus. Okay, so mostly since from different steps are there, so all these steps are basically we got from this and basically from this angle condition. Okay, largely you've seen on in the lectures also. So mostly steps are derived from this angle condition. Okay, so what is the step first? Step first is just locate the open loop poles and open loop zeros. For this, what you need? You need open loop transfer function. So GS into HS. Okay, so this will be given to you. So by looking at the open loop zeros and poles, first you can plot those zeros and poles here. Okay, this is the first step, right? And one thing, so since we are varying k from 0 to k to infinity, okay, so when does k occur? K equal to 0 is at this. So in this particular slide you can see for with the example. So this is the example we have seen. As k tends to 0, okay, s tends to pole. Okay, so here my 1 and -4 are the poles. So let me just highlight, these two are poles, right? So that's why we have marked as cross. Okay, so these two are poles, so where the value of k will be equal to 0. That's what this equation shows. So if you just see this equation, so when this since we know the characteristic equation 1 plus k, if you see this equation, okay, 1 plus k by s plus 1 into s minus 1 equal to 0. Okay, so it can be written like this: s plus 4 into s minus 1 plus k equal to 0. So when this equation becomes 0, okay, so when k is equal to 0, if you see s plus 4 and s minus 1, so s has to be equal to -4 and s has to be equal to 1. Okay, so then only this equation becomes 0. So what we can say, as k tends to 0, s tends to -4 and s tends to -1. Similarly, so how to find what will happen when k tends to infinity? So it is written in this form. Okay, 1 by k into s plus 4 into s minus 1 plus k. So as k tends to infinity, so 1 they have written 0 into s plus 1 and 0 plus s plus 1. So when k tends to 1, k tends to infinity, okay, this tends to 0. Okay, since they have written like this, so has to tend to infinity so that this whole term becomes 0. Okay, this is just a manipulation, so it can be much more appreciated when you look at this equation. Okay, because in this equation, so what I'm talking about is this equation. In this equation we don't have any 0, open loop 0. Okay, but if you see here, so let me highlight this. So this equation, so it has 1 0. Okay, 1 by k s plus 4 into s minus 1 plus s plus 1. So s plus 1, so this is 1 0. Okay, so when this equation becomes 0, when k tends to infinity and s tends to -1. Okay, so this is one condition. Another condition is when s tends to infinity. Okay, so it can be much more appreciated when k is infinity. It is at open loop pole, open loop zeros. Okay, so that we'll see. So in step 2, we have to locate the root locus on the real axis. Okay, so how to locate that? We'll see on which part you want to locate. Okay, so we'll take test points and we'll see how many open loop zeros and poles are there on the right hand side. Okay, so for this, like they have taken 3 test points, right? For ST1, if you see, there are two poles here. Okay, so that's why in this region, first region, this is second, this is 3, there are no root locus. So for the second test point, S2, ST2, ST2, so what is happening? There is only one pole here, right? If you see this region, okay, right hand side means this side. Okay, only 1 0, so that's why the root locus lies here. And if you take the third test points, so total number of poles and zeros will be equal to 0. So when I say poles and zeros, these are open loop transfer function poles and zeros, right? So that's why there is no root locus. Okay, so only root locus will be lying here like this. Okay, So that also we have seen in the lectures. And the step 3 is marking the asymptotes, right? So we have seen like how many uh, root locus we have, total n branches, right? So n is the total number of poles. Okay, so n branches and n m is the zeros. Okay, so n minus m root locus will tend to infinity. So those root locus will go to infinity. Okay, so for that we'll be finding out the asymptote angles and the intersection of those asymptotes. Okay, so that we have seen here. So this is the formula. So that these formulas have been derived by using angle conditions. Okay, and this intersection. Okay, that we'll see once we are doing the questions here. And again, break in and breakaway points. Okay, so when the root locus is breaking away from the real axis, okay, this is called breakaway point. Okay, so when the root locus is coming into the real axis, it's called breaking points. Okay, and how to do that? So we take the characteristic equation 1 plus k into as by bs. So if you see, this is the characteristic equation. Okay, and we just take this as equal to PCL. So if you see this, okay, and we differentiate it and find the root. Okay, so whatever the value of S we found, so that is the breakaway or breaking point. So how to confirm? So we have to also find the value of K, and if the value of K is coming out to be positive, then we'll say that particular point, S point, have is lying on the root locus. And what is the significance of that point? So we have multiple roots, right? So at this point, so let me just show you. So at this points, so this one you will have multiple roots here. Okay, so that's why that is shown with the derivation here. So why we are taking the derivation? Okay, the logic is this: we have multiple roots. So the first derivative of that, and if you take the first derivative and put that equal to 0, so the derivative will be 0. Okay, so that is already discussed in the lectures. Okay, then we find the angle of departure and the angle of arrival. These are only valid for complex poles and zeros. Okay, so that also you will do some questions here. I think one question. Okay, so the formula is this. Okay, formula is not given. I think they have given in the sheet. So formula angle of departure, so we'll be using this, is equal to 180 minus sum of angles made by opal loop. Okay, let me write opal loop poles plus sum of angles made by open loop zeros. So this is at what point we are trying to find out. Okay, so this is for poles, right? So we'll just, this is the formula, and exactly they have done calculation and they have written this. Okay, okay, so this is covered up to week 6. This is all we have covered up to 1 2 3 4 5, I think 5 steps we have covered. So this is 5 18. Okay, so any doubt in this, how to plot the root locus up to in steps 1 to 5? Okay, then I'll be going to the questions. Okay, so you take a test point and just satisfy these two conditions. If these two condition, magnitude condition and angle condition, and true, that means that particular point is lying on the root locus. Okay, that is what it is. Okay, let me go to the questions. Okay, so these are the questions that was in the assignments for the last group. Okay, so let me read the question. Consider a second order plant governed by this equation. It is desired to design a unity negative feedback closed loop control system with this plant using a proportional controller. So proportional controller is this. Cs equal to Kp, then closed loop stability will be achieved for, okay, so this is the plant equation. Okay, so let me first find the transfer function for this by assuming the initial condition to be equal to 0. Okay, that we all know. Okay, so P of S is equal to 1 by square plus 4s plus 3. Okay, so this is the plant transfer function. Okay, and what is CS? CS is Kp, proportional controller. Okay, and what is GS? GS will be PS into CS, or I should write CS into PS, right? So this will be Kp by square plus 4s plus 3. Okay, so this is block diagram. If you see, so this is CS, this is PS. Okay, so this is input RS. Okay, okay, so and I'm calling this as GS. Okay, I think HS is equal to 1. So unity negative feedback, that means HS is equal to 1. Okay, so that's why GS is CS into PS. Okay, so to find the closed loop stability, we have to find the closed loop transfer function. Okay, closed loop transfer function is GS by 1 plus GS into HS. Okay, so in this case HS is equal to 1. So what is GS? Kp by square plus 4s plus 3 divided by 1 plus Kp by square plus 4s plus 3. Okay, so this is Kp by square plus 4s plus 3 plus Kp. Okay, so this is closed loop transfer function. Okay, to find the stability, what we do, we consider the characteristic equation. Okay, so the characteristic equation is what here, let me call this as ds, okay, which is equal to the denominator s square plus 4s plus 3 plus kp. Okay, so this is the characteristic equation, and for this to be stable, for this closed loop transfer function uh, to be stable, what we want is its roots, or its roots are called poles. Okay, so pole should be lying in the this region, left half plane, right? So what do you want? So we have studied in the, while we are studying Rout Horwitz criteria, that for the second degree quadratic equation, for this quadratic equation, so necessary and sufficient condition. Okay, so what should happen? Necessary and sufficient condition, so its coefficient should be non-zero and of the same size or same sign. Okay, so if you look at this, okay, so coefficients are positive. So if you see the coefficient of s square, it is equal to 1, coefficient of s is 4, and this constant coefficient should also be non-zero, right? This 3 plus kp should also be non-zero, which should be positive, right? Then only we'll have all the poles, so it will have two poles, right? Degrees 2, so two poles, so both the poles will be in the right half plane. Okay, for that the constant term should also be greater than 0. Okay, then what is the condition on kp? Kp should be greater than minus 3. Okay, So if you have Kp proportional controller gain to be greater than -3, then you will be having roots. So this is imaginary real. So you will be having roots in this part. Okay. And if you have roots or the poles here, what we say, the system is stable, right? So if you look at this options, option 4 is correct. Kp should be greater than -1. Okay. So if you keep Kp greater than -3, then you ensure that the roots, there will be two roots. So both the roots will be lying on the left hand plane. So this is left half plane. Okay. So any doubt in this case? The plant equation was given. We found out the closed loop transfer function. Okay. Then by seeing its characteristic equation. Okay. So how to ensure that the poles are on the right hand side or left hand side? So we can just, you can also make the routes array also. Okay, if you're not clear, you can make the routes array and you'll get to this condition. Okay, where the first row of that, in the first row you'll get 3 plus kp, and you'll put that that should be greater than 0 for no sign change. Okay, so you'll get this. Okay, I think this was very simple question. So we'll go to the next question. So pollute transfer function in plant one is, again, this is, you tell me, you know, GSHS. So this is equal to Kp by S square plus 4S plus 3. So this is pollute transfer function. So what can you comment on the type of the system? Okay, what we say, type 0 means it type 0. Okay, correct answer is type 0. Okay, that means no open loop pole at origin, right? And for type 2, sorry, type 1, we know. So we have one open loop pole at origin. Similarly for type 2 and type 3. So type 2 have two open loop pole at origin, type 3 will have correspondingly three open loop pole at origin. Okay, so in this case, you can see there is no pole at the origin. That's why we are saying this is type 0 system. Simple. So this one, the static position error constant for problem 1 is, so you know what is position error constant. Let me write the formula. So this is the position error constant, right? So this is, you know, open loop transfer function. So Kp, so I should write Kpe. So Kp is limit s tends to 0. So GSHS from the first question is this. Okay, so this is GSHS, which is open loop transfer function, Kp by s square plus 4s plus 3. Okay, so if you apply the limit, what you will get? Kp by 3. So this is very simple. Okay, so third option is correct. So any question in this? I hope there is no question. It's very simple. Okay, limit, you have to apply the limit. That's it. The other one is the steady state tracking error when the stable closed loop system of problem 1 is provided a unit step reference input. Okay, so this is the closed loop. This is the block diagram for the closed loop plant. Okay, so in this case rs is unit step. Okay, so rs is 1 by s. Okay, so you know the tracking error is what? Limit s tends to 0, s into rs 1 plus gs into hs. Okay, I think we have also done in assignment 5 these types of questions, similar questions. Okay, so everything is known. Let me put the values here. S into rs is equal to 1 by s. Okay, 1 plus gshs from the previous question we know, which is kp by s square plus 4s plus 3. So kp by s square plus 4s plus 3. Okay, this is gs into hs. So let me simplify it before putting the limits. Okay, so this is s square plus 4s plus 3 square plus 4s plus 3 plus kp. Okay, if you put the limit, what you'll get? 3 by 3 plus kp. Okay, so ess is 3 by 3 plus kp. Okay, so what is the correct option? So option 2 is correct. Okay, so any doubt in this question? Very simple. So this is steady state tracking error. If you know this formula, just put in all the values. So rs is already given in the question, which is 1 by s. Okay, so this is unity step reference. Okay, which is equal to 1 by s. Okay, go to the next question. The steady state tracking error when the stable closed loop system of problem 1 is provided a ramp reference. So here the input is changed. Okay, ramp reference 1 by s square. So what is ramp? Ramp is like this. Okay, straight line. Okay, this is rt versus time, and you know rs is equal to 1 by s square. So again we'll be using same formula. So you have to find the steady state error, right? So formula remains same, 1 plus gs into hs. So gs is square plus 4s plus 3. Okay, so you know there will be one s term in the denominator. Okay, so this will be a square plus 4s plus 3. So s into this one, s square plus 4s plus 3 plus kp. Okay, so if you put the limit, what you'll get? 3 by 0. Okay, if you put the limit, what you'll get? 3 0 into, you'll get what? 3 plus kp. Okay, so it will tend to infinity, right? So ess in case of ramp, unit ramp will be equal to infinity. So any doubt in this case? Very simple. Okay, because of this is in the denominator. Okay, so again, so in this question they have asked the static acceleration error constant for problem 1. Okay, so what is that? So I'll write KAE. Okay, so limit s tends to 0. Okay, s square into gs into hs. Okay, just remember the formula. Okay, for the position it is that s is not there. Okay, velocity s is there, and for acceleration you have s square. Okay, and if you apply the formula, you know this is equal to kp into s square plus 4s plus 3. Simple. So it's, if you apply the limit, what you will get? So what is the answer? Can you do any manipulation?
Sir, option 3.
What you're getting? 0.
Yes.
Okay. So if you apply the limits in denominator, what you will get? 3. And in the numerator, anyway, you are getting 0 into kp by 3. Okay. So this is like 0. So again, option 3 is correct. Yeah, I hope there is no doubt. It's very simple. Okay, you have to apply the limit. That's it. Okay, now I think we have reached the root locus problems. Okay, so in this, let me read the question. The open loop transfer function of unity negative feedback closed loop system. Okay, so this is unity negative feedback. Okay, when hs is equal to 1, closed loop system is this. Okay, so this is open loop transfer function. Okay, for the closed loop system, s equal to -1 satisfy. Okay, so open loop transfer function is GSHS is known to us, which is s plus 1 square plus 4s. Okay, so where hs is equal to 1, that's given in the question. So for the closed loop system, s equal to -1. So if you look at the options, so we have to find out which condition it satisfies, magnitude condition or the angle condition. Okay, so you know, for the closed loop transfer function, this you know. Okay, and the characteristic equation is equal to 1 plus gs hs equal to 0. Okay, and the roots for this are the closed loop poles, right? And you know, gs hs equal to -1. Okay, so that is written, magnitude is 1. Okay, so just writing magnitude, and its angle is plus minus 180 degree, 2q plus 1. Okay, a q is from 0 1 2. Okay, so it has to, if any pole, okay, closed loop pole, if it satisfy this equation or the characteristic equation, then it should satisfy this also. Okay, this means if you put the value of s in GSHS, its magnitude should be 1 and its angle should be plus minus 180 degree, right? And for that particular s, what is that particular s that is given in the question? S equal to -1. So we have to check. Okay, for this value s equal to -1, we have to check whether GSHS's magnitude is 1 or the angle is it following both the condition or any of one condition. Okay, that we have to check. Okay, so if you put, you know, GSHS, let me write once again, which is equal to s plus 1 into s plus 1 into s square plus 4s. Okay, so if you put, let's first find the magnitude. Okay, so we are not putting s equal to sigma plus j omega, let's just put s equal to 1 -1. Okay, what you will get if you put, find the magnitude like this. So hs I'm not considering because hs is equal to 1. Okay, let me write hs is equal to 1. So whatever you put, you will get 1. Okay, so what you will get? -1 plus 1 minus 4s minus 4 you will get. Okay, this is, So if you say numerator minus 1 plus 1 is equal to 0. Okay. So we are not getting 1, right? So what we can say, so magnitude condition is not satisfied, right? So let's check for the angle condition. Okay, so what you will get here. So GS HS, let me write once again. It says S plus 1 S square plus, so I'll write S into 1 S plus 4. Okay, let me write this. So if you try to find the magnitude, so let's first put, okay, so what is the magnitude for this? Minus 1 plus 1, angle of minus 1, and angle of minus 1 plus 4. Okay, we're trying to find the magnitude, right? So let me write it clearly. So minus 1 plus 1. So I'm just putting s equal to minus 1 here and trying to find the angle. Okay, so magnitude I already calculated and just trying to find the angle of this. Okay, so what will be the angle for this? Angle of 0 will be 0, 0, right? And what will be the angle of minus 1 if you see the denominator? Minus 180. Okay, and for minus 1 plus 4 is 3, right? So angle will be 0, right? So what is the total angle? 0 minus 180. So this is plus 180, right? So if you go, it will be minus 180 minus 0. So the angle will be minus 180.
Hello, sir.
Yes.
Sir, angle will be 0, no, sir.
How?
Because numerator itself is 0, sir. If angle
Y-
condition is met, then
Yeah.
g of s, h of s will become minus 7, minus 4, minus 3. It will become angle is 180 degrees, sir. But if numerator is cancelling, how can we add the phases in denominator, sir?
If the numerator is getting 0, so I'm just taking the angle of each term in the numerator
Yes,
and the
sir. Yes,
denominator. That's it. So in the numerator, you're correct. The minus 1 plus 1 is equal to 0. Okay, just I'm taking the angle.
yes, sir.
Okay,
But if angle condition has to be satisfied, it will get negative values of real numbers, sir.
if
But
angle,
condition is met, then we have to get minus
mhm.
7, minus 4, minus 3 like that. If we get, then the angle condition is satisfied, sir. But here the angle condition is not satisfied, no, sir.
So I'm not getting your question because minus 7 you're saying, which value you're saying?
Minus 7, minus 4, minus 3
Acha,
if
in the numerator you're saying?
no, sir, if angle condition has to be met, then g of
Yeah,
s, h of s will become minus of
yeah.
real values, sir. But here
Okay.
it is the angle condition is not satisfied, no, sir.
I'm saying, let me check. You're saying if angle condition is to be set, then okay, minus has to be there.
No, sir, here the angle is 0, no, sir.
Uh, no, angle is 0. How it is 0? Like numerator, I'm just calculating for individual s terms. S plus 1, s into s plus 4.
No, sir, but angle condition here is 0, no, sir. Angle is 0, sir. S plus
Angle is 0.
1, yes, sir. Angle is 0, no, sir.
Uh,
I think for division you have to subtract the angle 0 minus 180.
No,
no,
sir.
no.
If angle condition has to be met, then 0, then the g of s, h of s would be minus of negative real values, sir.
that is fine.
But here we are getting 0 no sir, so angle is 0 no sir.
So you're saying GS HS should be equal to negative any value, like you're saying, let's so
Real
minus
value sir.
4. Yeah, then you're saying ki angle condition is met,
Yes sir, but
otherwise
here
it's
it
not
is
met.
0. Yes sir, but here it is 0 no sir, so how can we say that angle condition is satisfied?
Mhm. No, here, like, it's not a real value, right? It's in terms of S plus S terms.
Yes
Like you're
sir.
finding two condition, right? It's not that minus one. Here also you can say, okay, that's fine. Magnitude is 4, angle is minus 180 degree. But here you are finding like for different S terms, like how it cannot be like, I'm saying ki in this is special condition. If you plot this 0, okay, this point is like here. It can be like magnitude is 0.
Yes
Okay,
sir,
for this
but
condition, like GS HS. This is not S plane. This is GS HS plane. Okay,
yes
so
sir.
this S equal to 1. So GS HS can be this value, right? 0.
Yes sir.
So you can debate its angle is 0, its angle is minus 180 degree, whatever.
Yes sir.
Okay. So this is, you can debate it. Its angle can be 180 degrees. So according to our mathematical calculation, I am saying. Okay. So you can say,
Okay
okay,
sir.
0 angle is 0. It can be minus 180 also. That is fine. Because
Okay
0,
sir.
it's lying at the origin, right? So I'm
Yes
just,
sir.
I've done some mathematical analysis or manipulation onto this. So it's just basically how to calculate the angle. That's what it question is, like what we have to learn from this. Okay.
Okay sir.
So they have given a test point s equal to 1. So we have found out the magnitude to be 0. So if you find, like if you do further questions also, this is how you'll find the magnitude, right? So in the
Yes sir.
numerator, you will take just whatever the magnitude. So S. So in the further questions, you will be taking S equal to sigma plus j omega.
Yes sir.
Okay. So then you will take 10 inverse of omega by sigma. So that you will do. Okay. So here just you have to verify whether, so according to our manipulations, okay, so not seeing the magnitude, whatever, yeah, okay, just I'm calculating the angle here and I'm getting minus 180 degree. And that seems to follow, like it's matching with the option also, okay. So this option, the angle condition, but not, so it satisfies this one, the angle condition, but not the magnitude condition, okay. So if it's, let's assume some point does that, right? It's not, in this case, its magnitude is 0. Suppose in a particular case, your magnitude is not equal to 1, some non-zero value, okay? But its angle condition is met, okay? That, then what you can say about that point? So that point is not lying on the root locus, okay? That means it is not a pole of the closed loop transfer function, okay? Okay, so any doubt in this question? Okay, so we have calculated the magnitude and the angle. Okay, let me go to the next question. So let the open loop transfer function of negative feedback closed loop system be this. Okay, where k is non-negative real valued parameter. So here k is greater than 0. Then which one of the following statement is true about the locus of closed loop poles? So if you see the options, we have to find out the how many branches it has and how many of them terminate to open loop poles, terminate at open loop zeros. Okay, whatever. Let's see. Let's first plot the root locus. GSHS is given. Okay, k into s plus 1 into s cube plus 2s square plus 2s. Okay, so it can be written as, so s we take common from the denominator, you'll get s square plus 2s plus 2. Okay, so what can we say about the 0? Okay, zeros we have m equal to 1, right? Only one 0 we have, and that is at s equal to minus 1. Okay, only one 0 we have. And talking about the poles, so this is, we will be having three poles here, right? So if you see the degree of the this equation, s cube plus 2s square plus 3, so degree is 3, so we'll be having three roots, right? So one is lying at the origin where s is equal to 0. So s is equal to 0 is one of the pole. So we are talking about open loop zeros and poles. Okay, so sorry, I've written, so this is n equal to 3. Okay, and the other two roots, the other two poles can be found out by solving this equation. Okay, so we can use this formula, plus minus b square is 4 minus, okay, what you're getting, 4 minus 8 is minus 4, that is 2j. So 2j by 2 is 1, so minus 1 plus minus j. Okay, so s1 is minus 1 plus j and s2 will be minus 1 plus j. Okay, so here let me write like this. So z1 is minus 1, so here poles, so p1 is 0, p2 is minus 1 plus j, and p3 is minus 1 minus j. Okay, so let me highlight this. So this is 1 0, and these are three poles. Okay, and we have to, so how many root locus branches will be there? So we know total root locus branches. So tell me the answer.
Let's see.
3, right? So which will be equal to number of poles. Okay, so if you see the option only 1 and 2 and the last one D are correct. Okay, let me see. So there will be three root locus branches. Okay, so they will be originating from 0 and these two p1 p2 and p3. Okay, and so how many of them are will be going to the infinity? So how do we know? That will be n minus m. Okay, it will be 3 minus 1. Okay, so total number of root locus branches is terminating at infinity. Okay, which will be equal to two branches. Okay, so that's already covered in the lectures. So let us see the option. So which one of the statement is true? So it would have three branches. First option I am reading, it would have three branches. Two of them would terminate at open loop poles. Okay, so they originate from open loop poles, right? So this is wrong. So second option is it would have three branches, one of which would terminate at open loop 0. So this is correct. Okay, so we know root locus originates from open loop pole and terminates as at 0, right? Open loop 0. Okay, so it will have three branches. Okay, and one will be going to open loop pole and other two will be going to infinity. Okay, so this statement is correct. So any doubt in this question? Other options are, I think, incorrect. So let me read the third option. What it says, it would have four branches. This is incorrect. Two of which would terminate at open loop poles. And this is also incorrect. So last option is it would have three branches, all of which terminate at open loop poles. This is also again false. Okay, so we have 1, 0, 3 poles. Okay, and we'll be having 3 total number of root locus branches. Out of them, one will be terminating at open loop 0, which is said equal to -1, and again the rest of them, that is 3 minus 1, which is 2, will be going to infinity. Okay, so any doubt in this question? We'll make the root locus, then it will be more clear. Okay, so let me do the other question. Problem 8, the complex conjugate open loop poles are located at. Okay, so already we have found out. Okay, poles. So which is P2 is -1 plus j, P is -1 minus j. Already I have calculated in the previous question. Okay, so by solving s square plus 2s plus 3. Okay, so this is the correct option. So let's go to the next question. Problem with the region of the real axis that lies on the root locus is. Okay, so let's plot the open loop poles and zeros. Okay, this is imaginary, this is real. Okay, you know s equal to -1, we had 1, 0. Okay, and one pole is at origin. Okay, let me use the different colors. Okay, so this is at 0, and other ones are, these are the, okay, I'm getting one coming, ninth answer. Okay, so what is the problem with the ninth answer? Okay, in the ninth answer, so the complex conjugate open loop poles. So basically you have to find out the poles for this. So let me write it. I will directly return the, okay. So this is the open loop transfer function. Okay, what they're asking is open loop poles. So how to get the open loop poles? Solve this equal to 0. Okay, you know s square plus 2s plus 2. Okay, equal to 0. So what they are asking is complex conjugate roots, right? So one is at origin, and if you solve this s square plus 2s plus 2 equal to 0, okay, you'll get two roots, conjugate, this complex conjugate roots. Okay, so that's what I have done in the previous question. Okay, you see this? So this is the solution. So one of the pole is lying at -1 plus j, and other is lying at -1 minus j. So this is, okay, so that's what it was asking. So directly already we had calculated in the previous question, that's why I didn't solve. Okay, I hope it's now clear. So solution is s2, you will get -1 plus j, s3 you will get, so this is s1. Okay, minus j. I hope now it is clear. So let's plot the poles. So this is plus j, and this will be minus j. Okay, okay, so in this question what they're asking, the region of real axis that lies on the root locus. Okay, so let's consider three regions here, right? So we have first region from -infinity to -1, second will be from -1 to 0, and third will be from 0 to infinity. Okay, if you see, we'll apply the, so if you see the first region from -infinity to -1, okay, so if you take a test point here, okay, So you see from the test point, you see on the right hand side. So how many open loop poles and zeros are there? Okay, see to the right. So there are total two open loop pole and zero, -1 and 0, total 2, right? But for a root locus to exist, that number should be odd, right? So the root locus does not exist in this region, right? Minus infinity to -1. Okay, so here we root locus does not exist. Okay, so let me call this test point as st1. So if we take in the region 2 here st2, okay, so let me change the color. So this is st2. Okay, so you see to the right, what you can see, how many open loop zeros and poles you can see? One, right? So one is odd, right? So the root locus exists in this region, -1 to 0, correct? And if you take the other point here, st3, okay, and just see to the right. This is the right. So how many open loop poles and zeros exist? 0, right? So 0 is what? Not odd. Okay, so what can we say? The root locus does not exist here. Okay, so what we can say, the root locus exists between -1 to 0, right? So again, if I just draw -1 to 0, okay, these are two zeros. Okay, so what we have seen, root locus exists between this region. Okay, so if you see what is the correct option, -1 to 0. Okay, so any doubt? Okay, just take a test point and see to the right. If you are having odd number of open loop poles and zeros, right? Summation of poles and zeros. If that number is odd, what you'll say? Root locus exists between that in that region. Okay. So any doubt in this question? Okay. So we now know root locus exists between -1 and 0. Okay. We'll go to the next problem. In problem 8, the number of asymptotes. So this is equivalent to, I think, step 3. Okay. So number of asymptotes. So again, what is that number? Very straightforward. Can you tell me?
2, sir.
2, correct? So that is equal to n minus m, right? Number of asymptotes. Okay. So n is 3 minus m, just 2. Very simple. Because two root loci will be going to infinity. That's why we need two asymptotes. If you go to problem 12, the angle made by the asymptote with the positive real axis. Okay. So angle of asymptotes we have to find out. So what is that? I hope this is correct formula. Okay, so n minus m, just 2, right? plus minus 90 if I take q equal to 0. Okay, so there will be two asymptotes, so plus 90 and minus 90. So it is showing how much. Okay, you can say like it is 270 degree, right? So third option, 90 and 270 degree. So any doubt in this? Very straightforward. If you just take other values of q, you will be repeating it. Okay, taken 0 and you're getting 90 plus minus 90, so plus 90 and minus 90 you can write plus 270 also, no problem. Okay, so in problem 8, the point of intersection of assumed two. Okay, yes,
Sir, if n minus m is equal to 3, sir,
n minus m is equal to 3, yes,
then how is calculate the angle of asymptote?
okay, so we have this formula, right? 2q plus 1, how much you will get? 60 degree. So you have three asymptotes, right? So
Yes.
put the values q equal to 0, what you will get? So let me write q equal to 0. Okay, plus minus 60 degree. Okay, q equal to how much? You put 1.
Sir, two of them will be plus and minus 60 degree, and the third one,
Mhm.
about
You'll see that they'll repeat itself. So if I put q equal to 1, what you will get? 60 into, so this is 2 into 1 plus 1. This is 3, right? 60 into 3, then 180. Okay, you will get like this. 60, then this is minus 60, and this is plus minus, so you'll get 3. So if you put q equal to 2 again, you'll get the multiple of these two. So just check it. 60 into, then you will get 2 to 4 5. Okay, 6 5 is 300. Okay, so 300 is what? Again, this is 300, right? So let me first. So you got three asymptotes, right? 60, minus 60, and 180. Plus 180 or minus 180, what you can write. Okay, so if you put q equal to 2, what you will get? Plus minus 300. So same, it will repeat. Okay,
sir, how it is minus 180 degree?
minus 180 degree. Like just use this plus minus 60 into 3. 6 into 3 is 180, right?
Yes.
So exactly that you can take plus one. That is same like plus 180 degree or minus 180 degree, whatever you take, that is same, right? So I think there is a limit also, like how many you can take. For in case of 3, so what you took k equal to 0 and k equal to 1. I think if you take k equal to 2, then it will keep on repeating. What are the unique values of angle you're getting, right? Plus minus 180 degree in second. If you take q equal to 1, then you're getting plus minus 180 degree. Okay, if you take q equal to 2, then you'll repeat all the values. Q equal to 3, if you take again, it will repeat.
Yes.
Okay, so these are the unique values, 3.
Yes. And
Once you do, once you'll see like in the week 7 or week 8, so we'll be having assignment questions where we'll be calculating the angle of asymptotes. Okay, no problem. Okay, in this question, the point of intersection of asymptotes. So formula for that is the sum of, I think, sum of open loop poles minus sum of open loop zeros, right? By n minus n. Total number of poles minus total number of zeros for open loop transfer function. Okay. So we have, if you see z poles, let us first consider poles are at 0, minus 1 plus j, minus 1 minus j. Okay. And zeros, 0 is single 0 we have, I think minus 1. Okay. So let's put in this formula. So we have 0 minus 1 plus j. You can take the real part also anyway for the complex conjugate pair, you know, this will get cancelled. Okay. So minus of minus 1 by, so n is 3 minus 1. So this will be 2. So what you'll get, minus 1. So this is minus 2 plus 1 by 2. Okay, minus 0.5. So answer is minus 0.5. So angle of assumed twitch will be minus 0.5. Okay, so it will be like, if you draw the, so you're having 0 here. Okay, so minus, this is minus 1, this is 0. Okay, and I'm just drawing the asymptotes. So this is point of intersection of asymptote. Okay, so this is minus 0.5, and we have seen the angle is what, plus 90 degree and minus 90 degree, right? So again, this point is minus 0.5, just to show this is minus 90. Okay, so this is, up to now we know this is real, and also we know root locus exists between minus 1 and 0. Okay, that also we know. Okay, let's proceed to the, so any doubt in this, how we got to this point of intersection of asymptote? Okay, very simple. So this information we know up to now. So in the next question, which one of the following statement is true about problem 8? Break-in point between, okay, we have to find out whether there exists any breakaway point or break-in point. Okay, so one way how to do it, like, okay, so we always start from characteristic equation, right? So what is characteristic equation? 1 plus gs hs equal to 0. Like, let us start from there. So for the problem 8, so open loop transfer function was this one. Okay, let me just copy this. Okay, so this is gs hs equal to k into s plus 1 by s cube plus 2s square plus 2s. Okay, so if we write equal to 0. Okay, so what we used to do from here, how to find the break-in and breakaway point? First of all, what is break-in and breakaway point? Okay, so break-in, so this is valid for zeros, right? And breakaway for poles, right? But for breakaway, what happens when two of the poles lie on the real axis? Okay, and what is happening? They are going from real axis to the complex plane, right? Like in the conjugate plane, where it will have real value and the complex value. Okay, so like this. So you have seen like two poles exist, and the root locus is going like this. Okay, so this point we will call it as breakaway point. So these are poles, right? And for break in point, so breaking point is like, so okay, so let's suppose two zeros are there here. Okay, and let's assume a hypothetical condition where they are approaching the real axis here. Okay, so one is going like this and one will go like this. Okay, so I have just drawn the wrong direction. Okay, so actually this will be the case. Let us assume there exist two poles and like this. So let's suppose we have two zeros here. Okay, and let's suppose somewhere in the complex when we had poles, so poles are root locus is coming like this and it is approaching the real axis, right? So one will go here and the other will go here, so this will be breaking, right? And what is breakaway? We have two poles here, okay, and they are breaking away like this. Okay, so this is breakaway point and this is breaking point. Okay, so in our case, so let us see how our root locus is looking like this. So we have a pole, sorry, this is 0 at, for particular transfer function we have a 0, okay, and these are the poles. Okay, and we know root locus exists, that we know. Okay, and two of the root loci will be going to infinity along the asymptote, that we know. Okay, and we have to find whether break away point exists or not, or any point like you see. So what can you say just by looking at the above two examples here? Like breaking points means what? Two open loop zeros are existing on the real axis and root locus is coming in. Okay, so what can you say here? One open loop pole and one open loop zero is there. So is it matching with the above two graphs that you're seeing here? You just see. Okay, so this will be always the condition for breaking points and breakaway points. For our particular example, is it matching? At least you can say whether matching or not. Mathematically, we can prove whether any point exists or not, but just by looking at these graphs.
No,
Okay, so because for breakaway, break-in, let's take this break-in point. Okay, so break-in point you need two open loop zeros, right? We don't have that. And for breakaway point, what we need is two poles, open loop poles. But in this case, we have one pole and one zero. Okay, so we can say ki it does not exist here. So let's also prove mathematically. Okay, so how to prove mathematically? Okay, so we have this equation. Just try to get the equation in terms of S. Okay, so how to get this, which will be, so I'm just doing proper manipulation. So it will be -1, right? So K is equal to minus, so what we used to do now, do you remember this step? I'll not do it, I had already done it, so I'll just show you. So this step, okay, to find the break in and breakaway points. Okay, so you used to consider this. Okay, and we used to calculate this. So but no need to remember this, you can directly differentiate. So I think don't need to do this, you just have to differentiate like this. So you just consider this as some polynomial in terms of s, 1 plus k, s plus 1, this will be s cube plus 2 s square plus 2s. Differentiate this, okay, with respect to s, what you'll get 0 plus, so I'm writing full, okay, this will be square, and you'll get the numerator. Okay, so basically we have to put numerator equal to 0. Okay, so you'll get some numerator, I'm writing that separately. Okay, so ns will be equal to k into s cube plus 2s square plus 2s, okay, minus k into s plus 1, and also you can remove k also from here. Let me write ns as numerator as k into ns, this I'll not have k here. Okay, so basically I'll have s cube plus 2s square plus 2s minus s plus 1, and differentiate, if you differentiate denominator, what you'll get 3s square plus 4s plus 2. Okay, and if you put ns equal to 0, okay, so let me first find out how many roots it has. Okay, so it will be s cube plus 2s square plus 2s minus, so it will be degree 3. Okay, so 3s cube plus minus 4s square minus 2s plus minus 3s square minus 4s minus 2. Okay, so if you see, you have to put this as equal to 0. It will be equal to 0. Okay, so if you take the largest degree term s cube, right, so it will have 3 roots, right? So s1, s2 and s3. So if you solve this, you'll have 3 roots, and we have to find out for each root k1, k2 and k3. Okay, first of all we have to find out whether s1 and s2 are real or not, right? Break in and break away means if there exists any point, that means k is this s, any of this root will be lying on the here real axis, right? So it should be between -1 and 0, right? If not here, somewhere on the real axis, right? Because it is going to the real axis, right? So that should exist. So I've done one calculation, so let me show you. So yeah, so this is the calculation here. Okay, so I have just whatever I was doing, I had done the same. I have differentiated with respect to s. Okay, so this is s, and finally I was getting this equation quadratic. Sorry, its degree is 3. Okay, so it will have 3 roots. This one, if you see. Okay, so it will have 3 roots. So s1, s2, s3. So out of that, only one is real, and other two are complex conjugate roots. Okay, so s1 is coming out to be minus 1.6 and s2 is coming out to be minus 0.42 plus 0.65, so plus minus 0.65. Okay, so let me just copy the roots from here because we are interested in the roots. Okay, and I try to find the value of k for one of the real s1 minus 1.2. So I was getting minus 3.6, right? So again, what we conclude from here, I am getting s1, that is minus 1.6, and if I find k, I should get non-zero value, right? If it is a break-in or breakaway point. Okay, but I am getting negative. Okay, so, and if I do the same with s2 and s3, I'll get the negative value. So I have not performed that calculation. Okay, so let me go to the here. So these are the 3 roots. Okay, s1, s2 and s3. So if we see what I'm getting values, I'm getting here, one value I'm getting is here. Okay, so do you think at this point root locus can exist? So this is minus 1.6 something. Okay, so from the previous question we already concluded that root locus does not exist, right, at this in this portion. So let me just shade the portion. So here does not exist, right? Okay, and one of the point I was getting through solving the equation is this. Okay, and what I can do is I solved for k also. I was getting k something minus 3.6. Okay, so what that also says ki root locus does not exist, right? Also by looking at the graph we can say ki at this point there cannot exist a break-in or breakaway point. Okay, and also we can confirm by calculating the value of k also because I'm getting a negative value. Okay, similarly if I do for this other two roots s2 and s3, so let me call k1, I'll get something negative value. So this will be negative, and k3, this will also be negative. Okay, so what can I conclude? There exists no break-in and no breakaway point, right? So the option is last option. Okay, so directly by looking at this points we can say key break-in or breakaway point does not exist, but mathematically also you can prove it by doing like this. Okay, so any doubt in this question? Any doubt? You just see what first, what is the definition of break-in and breakaway points. Okay, and why it is not possible in our particular case. Okay, and also we can prove that by using this equation. Okay, finding first differentiating with respect to s and finding out 3 values because it's degree 3. Okay, and finding s1, s2 and s3. Okay, and correspondingly finding out the values of k1, k2, k3 also. So if you do that you'll get k values to be negative. Okay, so mathematically also we can prove there does not exist any breakaway or break-in points for this particular open loop transfer function. Okay, So the option, uh, last option is correct. Okay. So last is, in problem 8, the closed loop system would be stable for. Okay, what was JS? GS was k into s plus 1. So this was the open loop transfer function. K into s plus 1 is q plus 2s square plus 2s. Okay. So closed loop transfer function would be stable for all. So we have to again, so we have done many problems on that. So can you tell me how to find the stability for this? How do we ensure this? First, what are the steps like? How to go? How to find the value of k? So this is
1
open
plus
loop
g
transfer
of
function.
s. 1 plus g of s, sir. H
Correct.
of s is 1.
Correct. So we know closed loop transfer function is gs by 1 plus gs hs, right?
Yes, sir.
And for stability, what we used to do, we used to take characteristic equation, which is equal to 1 plus gs into hs, and we put that equal to 0, right? And we find out the roots, and those
Yes, sir.
roots are the closed loop poles, right? And if those closed loop poles for a particular value of k, we have to see those loops should be lying on the left half
Left
plane,
half.
right? Then we say
But
that
in but
particular
here
is, yeah.
but here it is done by s square and s coefficients multiplication should be greater than constant coefficient and s cube coefficient, no, sir.
Mm, here, repeat the question.
Yes, sir. 2s square plus 2s will be
Mm,
once right side equation s cube plus once right side
uh,
equation.
okay, let me first write 1 plus gshs, right?
Yes, sir.
Okay, so it shall be equal to sq plus 2 s square plus 2s plus k
Plus
into s
k.
plus 1, right?
Yes, then
Hmm.
s cube plus 2s square plus 2s k plus
Okay,
2 into s, sir. K
let me
plus 2
write
into
like
s
this,
plus k.
plus k. K.
Then 2 into 2 plus k should be greater than k, sir.
Okay, you are saying the answer.
Yes, sir.
Okay, we'll see. Oh, okay, so so this is characteristic equation, right? So this is degree 3, right? So let me just write it here. Okay, that you're saying is necessary condition, right?
Yes, sir.
Okay, so you're correct. Okay, so we have to find its root should lie on the left hand side of the S plane, right? So we have just remember that Hurwitz criteria that we studied. Okay, so for necessary condition, what we studied. Okay, so all the coefficients should be present and they should be non-zero and of the same size, same sign. Okay, so here in this case, all the coefficients are present and they should be non-zero, right? So that means 2 plus k and k should be 0, right? K should be greater than 0. Okay, then only they will be non-zero. So from here you're getting this condition, k should be greater than minus 2, and again k should be greater than 0. Okay, and for sufficient condition, what we used to do, okay, we used to construct Routh's array, right? So s cube s square S1 is 0. Okay, so this is 1 2 2 plus k and k. Okay, so the coefficient of S1 is 2 into 2 plus k minus k by 2. Okay, and for this you'll get k. So you know how you got this, right? You first multiply 2 into 2 plus k minus 1 into k by divided by 2. Okay, and what we have to ensure, there is no sign change. Okay, in this first column. Okay, there shouldn't be any sign change. So for that, what we ensure is this term 2 plus k minus k should be greater than 0, and already k should be greater than 0. Okay, then only we ensure there is no sign change. Okay, so if you solve this, what you'll get, so this is numerator, right? 4 plus 2k minus k should be greater than 0, and this is 4 plus k greater than 0, and k is what you're getting, 4. Okay, so this condition you're getting from here, if you put k greater than minus 4, okay, and k greater than 0, so this is and condition, right? So we cannot have k greater than minus 4. Okay, if you take the intersection of these two conditions, so what we have is k greater than 0. Okay, so necessary condition k greater than, again, if you take intersection, we will have k greater than 0, right? So if we ensure k greater than 0, so what we'll have, if you say, we'll have all the values of this first column to be greater than 0, right? Although if we ensure k greater than minus 4, this value would be positive. Okay, but for minus 4 to 0, this will be negative. Okay, thus, so we want all the elements of first column to be positive. Okay, that's why if we ensure k to be greater than 0, what we are ensuring is all the values are greater than 0, non-zero, sorry, yeah, greater than 0, which are non-zero, and the poles, if you will find, so those poles will be in this side. Okay, and we can say the system is stable. Okay, so any doubt? So this is again stability problem that already is being covered, I think, in assignments also, previous assignments. So any doubt?
Sir, in assignment questions there is negative marking, sir. Is there a negative marking, sir, in assignment questions?
That I don't know, because we are not checking it. So I think negative marking is okay, because for the previous semesters we can see like they will give plus, like positive plus marks, and I think plus 2 or minus something was the one third they are deducting something. For you, I don't know like exact what is the negative marks.
In exam, sir, in exam.
Uh,
What about in
exams.
exam?
So exam is objective or subjective?
Objective, sir.
Objective. I think then there will be negative marks. That, but I cannot confirm that.
How can we know, sir?
You can mail to the coordinators. Like,
Which coordinate, sir? Who,
so
sir?
do you have any email address for NPTEL? Like, you have, if you have subscribed to this course, any email address?
Yes, sir. Support at the rate of npteliitm.ac.in.
So you have sent the mail for to them asking about this positive or negative marking.
No, sir, I didn't send, sir.
Okay, just send. If you're not getting any reply from them, I'll ask them. Okay, because I don't know because we are not like on that checking and on this thing. She don't know.
Okay, sir.
Okay, so any doubt in this question?
No,
Stability
sir.
question is typical question that was I think already we have covered in the previous assignments also.
No, sir. No, sir.
Okay, so okay, one more thing is for the question number 8. Okay, because since we have not drawn the entire root locus, so shall we find out the, so let me just add angle of departure. So first you tell me, okay, so you can see here, just focus on these two poles, okay, complex poles, right? So what can you say? They will have angle of departure or angle of arrival. So what should I calculate,
Angle of departure, sir.
right? Because for
Yes,
the
sir.
poles we calculate angle of departure. Okay, so let's calculate that. Okay, which is what, 180 degree minus sum of, I think what, open loop poles. This is angles, right? So what I'm saying is which angle. I'll just mark and tell you. Okay. So let's assume you want to calculate the angle of departure for any one pole. Okay. So let me mark that. Let me name this. This was pole 1, this is pole 2, and this is pole 3, right? So let me copy this. Okay. So now what you want is, for P2, you want to calculate the, so let me call this as P1, not P2. P1, this is P2. Okay. So angle of departure. So one thing, let's first make this one first root locus. Okay, you know the root locus goes from pole to 0. Okay, so I'm making this pole to 0. Okay, so one of the root locus will be going from P1 to this one. Let me call this as Z1. Okay, because there will be no breakaway or breaking points. The only path it will cover is this one, because also we have seen from -1. So if I write the values, this is -1 and this is 0, right? And we have seen from -1 to 0 root locus exists. Okay, so I have drawn one of the root locus, so it's going from 0 to -1. So value of k equal to 0 to k to infinity. Okay, so this I have drawn. So rest, so total 3 branches will be there. So one is originating from P1, other will be from P2, and the last one will be from this one P2. Okay, so I'm just calculating here angle of departure, like how it will originate and go to infinity. Okay, like it can go like this, because it also, let me make the asymptote. This is asymptote, this line is asymptote that we have seen, is minus 0.5. Okay, and the root locus will be going along this path. Okay, but what is the angle of departure? How they can go like this, right? And other ways it can go like this. Okay, so what is that angle? This angle, this angle. That's what we are calculating here. So for P1, let's calculate the angle of departure here. Okay, so angle of departure for P1 I will write. So 180 minus sum of opposite pole angles. Okay, so there are two poles here, right? P1 and P2. So what is the angle they are making with P1? Okay, let me draw with this. So one is this. So this is one angle, right? And the other angle will be this one. This will be another angle. This is with respect to 0. This will be one angle and we have to add this. So I'm writing this angle as P1 and P2. Okay. Okay. So this is not P1. Just let me call this P0. Okay. So these two angles I have to calculate, and I will write here theta P1 plus theta P2. Okay. And what 0 is making? So okay. So pink color is what this 0 is making with P1. Okay. So this is the angle that is making. So I'll just okay here. Okay. So this angle. So I'll make it bigger. So angle Z1. Okay. So this is plus. Okay. This is plus angle Z1. So that's what we have to calculate. Then we'll get the angle of departure. Okay. So let's calculate theta P1. Okay. So what is that? You know, theta P1 is what? 90 degree plus this angle.
135 degrees, sir.
Yeah. So if you calculate, this is 1, this is also 1. Okay. This is 1, 1. Then this angle is 45. Okay. And what this angle will be? 180 minus 45. Okay. Which will be 135. Okay. So I'll write t minus theta 1 is 135 plus what is theta P2? Theta P2 will be 90 degree. You see? Okay. You see this and this. Okay, this is P1, this is P2, and what is the angle it is making? You see, 90 degree, right? With respect to positive, this if you consider this as 0. Okay, and what is again theta Z1? So for theta Z1, let me draw again one diagram. This is P1 and this is your Z1. Okay, so what is the angle they are making? Again 90 degree. Okay, so this is plus 90 degree. So if you solve this, okay, so this is plus. So what you'll get is 180 minus 135 is 45 degrees. So angle of departure for P1 is 45. Again, if you try to calculate angle of departure for P2, you'll get minus 45. Okay. So let me just draw it again. So how that will be. Okay. So this is one of the root locus, and this is the asymptotes. Okay, 90 degree, and this is minus 90 degree. Okay, and we have calculated the angle of departure. Okay, so it will be making like this. So this angle will be 45 degree, and it will be going to infinity like this. Similarly, if you see here, and it will be going to infinity. So if I make it, yeah, like this, and this angle is minus 45 degree. Okay, let me complete this. So this is how the root locus will look like. Okay, so this is minus 1, this is 0, and this is minus 1 plus j, and this is minus 1 minus j. Okay, so this is how the root locus will be looking like. So there will be 3 branches. Okay, so you can so let me just point out, this is branch 1, this is branch 2, and this is branch 3. Okay, so you can see one branch is going from pole to 0. Okay, so pole is 0. Here you see this is pole. Okay, and this is 0, and the other 2 branches are going from pole to infinity because we don't have 0. Okay, so they will be terminating at infinity. Okay, so let me write the values of k also. So here k is equal to 0, here k is infinity, and again here k is equal to 0. Again at infinity it will be infinity. Okay, so this will be the root locus for this. So any doubt? So this is the final root locus for this transfer function that was given to us. So one pole and three, sorry, 1 0 and 3 pole. Okay, so any doubt? Okay, and we can say that if we have, this is stable system, right? So all the poles are lying on the left half plane. Okay, so any question for any doubt for any question for today's session? Okay, simple question we have done, like on different steps to make the root locus. Okay, and many more questions are to come in the next, because still this topic is not finished, right? So like crossover points and all this. So finally we'll see a lot more questions on this maybe in the next assignments. Okay, any doubt? Okay, if you are having no doubt, then I'll end the session. Okay, we'll meet in the next session on Tuesday, same time. Okay, go through the videos for week 7. Okay, then we'll be doing questions. So thank you for attending the session. Thank you guys. Thank you.